Lindsay.
Hi, my name is Stefan.
I'm Journey, and we're doing our video on Dive-namics.
We're doing our video on moment of inertia and angular momentum of diving. Let's dive in!
Today, we will show you 3 relatively basic dives and how moment of inertia and angular momentum play a role in each one. Clearly, every dive could be turned into incredibly complex dynamics problems way beyond the scope of ME 212, so we will be simplifying everything to focus on a couple of topics we actually studied this quarter.
The first dive we analyze is called a front 2.5 tuck. Once the diver applies a force on the board and is launched into the air, angular momentum is essentially conserved for the duration of the dive due to the law of conservation of momentum. Angular momentum is moment of inertia multiplied by angular velocity. If Stefan cannot change his total angular momentum after he has left the board, how can he maximize the number of rotations he does in the short amount of time that he is in the air? He can change his moment of inertia. Moment of inertia depends on mass and the radius of gyration. Stefan can't change his mass, but he can control the radius of gyration by pulling his body into a tuck, thereby decreasing his moment of inertia and increasing angular velocity.
Freezing Stefan in mid-air, let's model him as a rigid body and draw the necessary diagrams one would use when solving an angular momentum problem. We start with a free body diagram and realize that once Stefan starts rotating, gravity is the only force acting upon him. At the beginning of rotation, we will model Stefan as a slender rod of 140 pounds that is 5.5 feet in length because he is 5.5 feet tall. This would give him a moment of inertia of approximately 353 pounds square feet. The start of his rotation is catalyzed by an internal torque that he creates with the throwing motion of his arms, but let's simply realize that this brings his angular momentum from a value of 0 to something greater than 0. This elevates his starting angular velocity up to, say, 1 radian per second. As shown, this will give him an angular momentum of 353 pound-feet per second. There will also be translational components to his velocity in the x and y direction that carry him away from the board, but in this problem we will ignore them since they do not affect angular momentum. Now, as he begins to spin, Stefan will draw his arms and legs closer to his center of rotation to decrease his radius of gyration, and we will now model him as a sphere. Radius of gyration is the square root of the moment of inertia divided by mass, and since Stefan's mass does not change, radius of gyration and the moment of inertia are directly proportional, so we can expect his moment of inertia to decrease. In application, we will use the law of conservation of momentum and set the total momentum at the start to the total momentum at the end. As an approximate sphere, Stefan's radius was measured to be about 1 foot. Therefore, his new moment of inertia, using the equation for a sphere, will be about 56 pounds square feet, a value that we can now see is substantially smaller than the first. When we solve it, we find that Stefan's new angular velocity in the tuck position is 6.3 radians per second. So, by drawing his arms and legs in, Stefan can make himself rotate significantly faster.
In the second dive, Kenzie does a front 2.5 pike. Again, the diver changes the moment of inertia by changing the radius of gyration. If she were frozen in mid-air and put into a before and after free body diagram, she would go from a slender rod to a shorter slender rod. Entering the pike position causes the diver's angular velocity to increase, but to a lesser degree than going into a tuck, as in the first dive. Comparing these two dives shows how the radius of gyration relates to angular velocity and thus the difficulty of the dive. Front 2.5 pike is harder to perform than front 2.5 tuck because the diver needs more initial force to complete the maneuver.
The third dive is called a front 2.5 straight and is the most difficult of the dives shown in this video. The higher degree of difficulty is due to the fact that theoretically, the diver's moment of inertia does not change because they remain in the same slender rod position without changing the length. In this video, the diver curls his body in a little bit, but perfectly performed, there would be no change in length.
To recap, moment of inertia depends on 2 things. Number 1, the mass of the object or diver, and number 2, the radius of gyration or the distribution of mass from the axis of rotation. Divers change their body position to alter the radius of gyration, which in turn alters their moment of inertia and angular velocity, which affects the difficulty of a dive. The smaller the radius of gyration is, the faster their angular velocity will be, and the easier it is to complete a certain number of rotations. Tune in on the next episode where we'll study the sport of Division 1 belly flopping by learning about impacts.
Thanks for watching!